Hi, it's Paul. I misspoke when I said that script 11D was the last Math 156 script. I forgot about script 11P. A couple of very nice examples involving a uniform distribution, one for a location parameter, one for a scale parameter. So let's start with the easier of the two cases. We will invent a uniform distribution with a location parameter. The way we're going to do this is to generate numbers according to a uniform distribution that runs from theta minus 1 to theta plus 1. And for the sake of concreteness, I will use theta equals 3. Then x minus theta is a uniform distribution on minus 1 to 1. That doesn't depend on theta or on any unknown parameters. That means that x minus theta is a pivotal statistic, and theta qualifies as a location parameter. So now we can construct a 90% confidence interval. Let's get the 5% quantile for a uniform distribution running from minus 1 to plus 1. What do you know? It's minus 0.9. We didn't need r to figure out that if we're generating a number between minus 1 and plus 1, it has a 95% chance of being greater than minus 0.9 and only a 5% chance of being less than that. It's also equally obvious that it has only a 5% probability of being greater than 0.9. But let's test our general methodology for constructing confidence intervals from location parameters. We'll generate a random number from this distribution, and to calculate the lower end point of the confidence interval based on the general theory of location parameters, we take x minus q2. To get the upper end point, we take x minus q1. q1 was a negative number because we're drawing from an interval that runs from minus 1 to plus 1. Now that we're sure that we are computing reasonable values of f, l, and u, we can do it 2,000 times. So generate a random number from the uniform distribution that goes from theta minus 1 to theta plus 1. That'll be between 2 and 4. Having got our sample, we subtract q2 to get the lower end point. We subtract the negative number q1 to get the upper end point of our confidence interval. If the actual parameter is less than L, the low end point was flawed, so we'll count a miss on the low end. If the true parameter is greater than our upper end point u, we missed on the high end, and we will score an error there. Otherwise, we'll score 1 for correct. So let's try it. And things worked out fairly nicely. We missed on the low end 102 times, on the upper end 87 times, and our confidence interval captured the 2 parameter 1,811 times, which was roughly the 90% we were shooting for. Rerun this, of course, and you'll get different numbers. Now here's a more subtle one, a uniform distribution with a scale parameter, and I would suggest that if you haven't already done so, you go look carefully at example 7.13 in the textbook, the so-called German tank problem, and then return to this video. Fine, you're back, right? You know all about the German tank problem. And what we're doing is collecting n samples from a distribution that's uniform in 0 up through some parameter theta. In the German tank problem, theta is the serial number of the tank most recently produced by German industry. We know that a good way to estimate the upper end point of a uniform distribution is to take the largest sample we've observed and then multiply by n plus 1 over n. That's an unbiased estimate of theta. And furthermore, we know how to calculate the distribution of this statistic. It's n times y raised to the n minus 1 power, which is an example of a beta distribution. Alpha equals n, beta equals 1. Furthermore, this distribution doesn't depend on the value of theta. It's just a beta distribution with parameters that never mention theta. So the maximum observed sample divided by theta is a pivotal statistic, and theta qualifies as a scale parameter. This is treated in detail in the second half of proof 2, and if you haven't studied that, you might want to stop this video again and look at that before we do the simulation. Good, you're back, you know the theory. Now we're going to do the simulation. Let's use theta equals 100. In other words, we're generating random numbers uniformly distributed in 0 to 100, and we're drawing a sample of 10. To get the appropriate quantiles, we exploit the fact that this is a beta distribution, and R has the function Q beta at our disposal. So we get Q1 and Q2. That means that 5% of the time we will get something that's less than 0.69, and 5% of the time we'll get something that's greater than 0.997. Okay, we're going to compute a confidence interval from the sample. I always like to try this out in one case where I can look at the details. So there's x. That's the maximum of the 10 samples from our uniform distribution. There is our beta distribution, which gives the distribution of x divided by theta. There's a blue line that marks off the 2.5% quantile. There's a probability of 2.5% that the largest sample we get will be less than 69% of the maximum. There's the upper quantile at 99.7%. There is a 2.5% probability of getting a largest sample that's greater than 99.7% of the value of theta. And there's our actual value of x over theta. What we do with x is multiply by n plus 1 over n. That's our unbiased estimate of theta. And we now know the probability distribution for x over theta. It's got a beta distribution. We know its quantiles. And so we can calculate the lower and upper bounds for the confidence interval. We take our sample, divide by Q2 to get the lower end point at 91. We divide by Q1 to get the upper end point at 131. And we say this interval now has a 95% chance of including theta. So on the basis of this one sample of 10 units, we say that we're 95% confident that the upper end point for this uniform distribution was somewhere in between 91 and 131. Our actual estimate is not smack in the middle of this. Our estimate was equal to 99, and the middle of this interval is 111. And if you look back at proof 2, you'll see this is typical of solutions to this problem, that the estimate is nowhere near the middle of the confidence interval. But let's see if it works. We can afford to do 4,000 trials in a reasonable amount of time. And here we go. This generates our sample of 10, extracts the maximum from it, multiply that by n plus 1 over n. That is our unbiased estimate of theta, the upper endpoint. We divide by Q2 to get the lower endpoint, something that is very likely to be smaller than theta. We get a U, which is very likely to be greater than theta. And then we see how we've done. If theta is in fact smaller than n, L, we missed on the low side. If theta is greater than U, we missed on the upper side. Otherwise, we were correct. And we might as well display 100 examples of this. And let's see what we got. First, let's look at the display. As usual, red is the estimate that we computed from the maximum sample. The horizontal line is the confidence interval. Notice these confidence intervals differ quite strikingly in their length, and furthermore, the estimate is nowhere near the middle of the confidence interval, but this is the theoretically correct confidence interval. Let's see how we did. Well, most of the time we managed to capture the true value of theta, but you can easily spot a couple of examples where the entire confidence interval lay to the left of the blue line, and I don't think there are any here where it lay to the right, but that's just we only looked at 100, so who knows. But from the full 4,000, we see 98 times we missed on the low end, 100 times we missed on the high end, 3,802 times we were correct. So we did indeed construct a beautiful 95% confidence interval for this distribution.